Hello and welcome to tutorial 14. Our topic today is an introduction to energy in chemical reactions. Before we get started, just a quick reminder that the notes to accompany this video tutorial are available online through my website. And with that said, let's get started today with collision theory on slide 2. So right up here on the board, collision theory. And we are just going to briefly cover the three main points from collision theory. The first being that molecules must come into contact in order to react. And they come into contact through collisions. So let's write for number 1. Molecules must collide in order to react. But these near collisions do not always result in a chemical reaction. In many reactions, the orientation of the molecules is also important. The orientation of the molecules needs to be such that old bonds are in a position to break and new bonds are in a position to form. So let's write down here for point number 2, molecules must have the proper orientation for a reaction. So let's just look at a quick example for this. Let's look at the reaction between ozone and nitrogen monoxide to form oxygen and nitrogen dioxide. And I'm going to draw just sort of a cartoonish diagram here to represent my molecules. I will draw 3 spheres to represent the 3 oxygen in ozone. I'll make those black. And then for nitrogen monoxide, let's make our nitrogen kind of stand out here. Let's make it green. And the oxygen again, we're going to make black. And then over here in our product, oxygen, diatomic molecule. So I'll put 2 black spheres here. And then again, my nitrogen is green. And nitrogen dioxide has an oxygen on each side of the nitrogen. So I'm going to put a sphere, a black sphere, to represent those 2 oxygen, one on each side of the nitrogen. Okay. So as long as a collision that's occurring between the ozone and the nitrogen monoxide occurs such that the oxygen at the end of the ozone is colliding with the nitrogen from the nitrogen monoxide, then we can see that the old bond is in a position to break. Old bond breaks. And this new bond between the nitrogen and the oxygen, this new bond is in a position to form. So I'll just indicate here, new bond forms. And this reaction will proceed. But let's flip that nitrogen monoxide around and look at this second scenario here. So I'll redraw the ozone, and now I'm going to draw the nitrogen monoxide where the nitrogen is oriented away from the ozone. And so we can see with this orientation that this collision is simply not going to put the nitrogen in the correct position for the old bonds to break so the new bond can form. This collision is not going to result in a reaction. Okay, so our third and final point from collision theory is that these collisions must possess enough energy for the reaction to occur, where that energy is really referring to the kinetic energy of the molecules. And that energy, that kinetic energy, can be used to break apart the old bonds so that the reaction can proceed. It always takes energy to break a bond. Some bonds that are more stable, it's going to take more energy to break them. Some bonds are less stable, so it's going to take less energy to break them. But it always takes some amount of energy to break a bond. And therefore, every reaction will have a minimum amount of energy that is required in order for that reaction to proceed. We call that minimum amount of energy the energy of activation, and we abbreviate it capital E of little a. I'm going to write that down here. Okay, so point number 3, every reaction has a minimum amount of energy that is required to break apart bonds and get the reaction going. And we call that minimum energy the activation energy, and we abbreviate it capital E little a. Okay. All right, so we are going to go ahead and erase here and go on to slide number 3 and talk about the law of conservation of energy. The law of conservation of energy tells us that energy can neither be created nor destroyed, but it can be converted from one form into another. Now, molecules have a chemical potential energy stored in their chemical bonds. If a molecule is high in this type of energy, we say that that molecule is more reactive, less stable. It is more likely to undergo a chemical reaction and release some of that energy. If a molecule is low in this type of energy, that molecule is more stable. It is less reactive. Now, in a chemical reaction, the energy of your reactants is probably not going to be the same as the energy of your products. And so chemical reactions will occur with a change in energy. And this can really happen in one of 2 general ways. The first possibility is that the energy of your reactants is higher than the energy of your products. So I'm going to label this R for reactant and this one P for product. And the y-axis here is representing energy, and the x-axis is representing my reaction progress. And the conversion of reactant into product. The other possibility is that the energy of the reactants will be lower than the energy of the products. And again, I'll label this energy and Rx in for reaction, progress. Okay, so let's talk about each of these scenarios in a little bit more detail, and we'll start over here. Okay, so we already know that every reaction has a minimum amount of energy that is required to get that reaction going, to start breaking apart the bonds in the reactant, and we call that energy the activation energy. So I'm going to go ahead and start out by indicating that activation energy. And that activation energy can be greater for some reactions, it is lower for other reactions, but we're just being generic here with our energy diagram. So I'm just going to indicate some activation energy barrier there. All right, so if the energy required to start breaking apart those reactants is less than the energy that is released in forming the product, because those products are more stable, they are lower in energy, then that reaction will occur with a release in energy. Energy will be released in some form. So I'm going to write here, energy is released. And this is what we call an exergonic reaction. I'm going to write that here. An exergonic reaction. And we designate the energy that is released as delta G. And we get it from the difference between the energy of the reactants and products there. So that's what this is supposed to be representing. And for an exergonic reaction, the delta G will be negative. That negative sign will tell you that energy is being released rather than absorbed. And delta G, just really quickly I'll write down here, the delta G stands for the change in Gibbs free energy. And it takes into account the heat of the reaction, as well as something called the change in entropy, where entropy is a measure of the amount of randomness or disorder in a system. Now let's go ahead and take a look at a specific reaction that is an exergonic reaction. And a great example is any combustion reaction. Well, we'll go ahead and do the combustion of methane gas, CH4, which is one of the main components in natural gas. And in combustion, it combines with oxygen to form carbon dioxide and water. Two very stable, low energy products. Let's go ahead and balance this here. Don't want any unbalanced reactions, so we're going to put a 2 here, and let's see, we also need a 2 here. Okay. Now this is an exergonic reaction, so to show that, I'm going to go ahead and just generically put plus E for energy. Energy is released. It's released in this chemical reaction. And in a combustion reaction, you're probably familiar with that energy being released in the form of heat and light. And we utilize that heat for a variety of different uses. We use it to cook our food, we use it to heat our homes, power our cars. In the case of cars that run on natural gas anyway, this reaction is a very useful reaction. All right, so let's go ahead and talk about the other possibility. When our reactants are lower in energy than our products. So in this case, again, we're still going to have that activation energy barrier, that minimum amount of energy that is required to get the reaction going. Depending on the reaction, that activation energy can be greater, it can be smaller, but we're going to be generic here. So I'm just going to indicate some energy is required for this reaction to get going. And because in this case, that energy required to start breaking apart the bonds of the reactants is greater than the energy that's released in the formation of these higher energy products. In this case, energy must be absorbed in order for this reaction to proceed. So I'm going to write here, energy is absorbed, and we call reactions that absorb energy endergonic reactions. I'm going to write that here. It's an endergonic reaction. And the delta G in an endergonic reaction is always positive. So positive delta G. Okay. All right, so for an example of an endergonic reaction, I like to use photosynthesis because it's a reaction that so many people are already familiar with. So let's go ahead and erase just this little bit of information here about Gibbs free energy. Give myself just a little more room here, and I'm going to write photosynthesis. You know, I think I'll even switch to a blue pen because it's getting really busy up here on the board, and this will make it stand out from our combustion reaction over here, our exergonic reaction. Okay, so photosynthesis, and photosynthesis, carbon dioxide and water are combined to make the higher energy molecule, the more ordered molecule, glucose, C6H12O6, and oxygen. Oxygen is also produced. I'm going to balance it by putting a 6 in front of the oxygen, a 6 in front of the water, and a 6 in front of the carbon dioxide. Okay. So where does the energy to produce that higher energy, more ordered molecule come from? Well, you probably already know that in this case, the energy comes from the sun. Right here, sunlight. Okay. All right, so we are just being generic here. I'm just writing energy, but really there is a specific quantity of energy that needs to be absorbed for this reaction to proceed. And that energy is typically expressed in either kilojoules per mole or kilocalories per mole. So I'm going to go ahead and write for this particular reaction, photosynthesis, that the delta G, that energy, is positive 686 kilocalories per mole of glucose. Okay, so a specific quantity of energy needs to be absorbed for that reaction to proceed. Now, the reverse of an endergonic reaction is always going to be an exergonic reaction. And the amount of energy that had to be absorbed for that endergonic reaction is the same amount of energy that will be released in the reverse exergonic reaction. So let's go ahead and take a moment to write the reverse reaction here, the combustion of glucose, which will be an exergonic reaction. So let's write it over here on this side. Okay, so we have the high energy glucose molecule, C6H12O6, combining with oxygen to form the lower energy carbon dioxide and water. I'll put a 6 here, and a 6 here, and a 6 here, and plus energy. Energy is released. So I'm going to indicate energy is produced in this reaction. How much energy? Well, we know that the delta G must be negative 686 kilocalories per mole. Now, this reaction is a very interesting reaction to look at here, because this reaction is the overall reaction by which glucose is broken down during cellular respiration. And so you might be thinking, well, combustion reactions, they release a lot of heat energy. Wouldn't that be detrimental, even fatal, to our cells? And the answer is that if this reaction occurred the way it does in a regular combustion reaction, releasing all that heat energy all at once, it would be detrimental, even fatal, to our cells. But within the cell, this reaction takes place over a large number of steps. First, there are the 10 steps of glycolysis, by which glucose is converted into 2 units of pyruvate. That's followed by pyruvate oxidation, where pyruvate is converted into acetyl-CoA, acetyl coenzyme A. Acetyl coenzyme A then enters into the Krebs cycle, series of yet another bunch of reactions to convert the carbons in the acetyl portion of the molecule into carbon dioxide. And then high energy molecules, electron carriers, go through a series of reactions in the electron transport chain, losing their energy and ultimately combining with oxygen from the air that we breathe to make water and providing energy to power oxidative phosphorylation. That is the phosphorylation of ADP into ATP. So a large number of reactions to get from glucose all the way to carbon dioxide and water. So let's just show those reactions on this energy diagram and sort of compare it to this reaction happening all at once here. So I'm just going to draw one little lump to represent energy being released during glycolysis. So I'll label that glycolysis, which is actually a 10-step process, but I'm kind of simplifying here. And that's followed by some more energy being released during pyruvate oxidation. And if you don't know anything about these processes, glycolysis, pyruvate oxidation, the Krebs cycle, electron transport chain, and oxidative phosphorylation, tune in to a future tutorial where I will be covering all of that. And I gotta tell you, that is, at least in my opinion, where chemistry gets really, really fascinating. So I do hope you will tune in for that. Okay, so a little bit of energy released in pyruvate oxidation, more energy released in the Krebs cycle, followed by, I'll just write it all here, the electron transport chain and oxidative phosphorylation. I'm going to abbreviate OXF because I'm really running out of room here. But ultimately, the point of all this is that although this reaction is happening over a number of steps rather than all at once, the change in the energy is still the same. You still get the 686 kilocalories per mole of glucose that is oxidized, okay? But the energy is released slowly, in a controlled way, little bits at a time. And some of that energy in cellular respiration is released as heat, but a lot of it is utilized to make high energy molecules. It's stored in the chemical bonds of these high energy molecules. The most common one being adenosine triphosphate, ATP. So I'm going to write here, for this energy here, in cellular respiration, that energy is released not only as heat, but also released and stored in the chemical bonds as chemical potential energy in high energy molecules like ATP. Okay, so pretty neat stuff. All right, so last thing I want to talk about here, and then we are going to move on to our final slide, slide 4. I want to talk about 2 terms that people very frequently will confuse with the terms exergonic and endergonic. So I want to go ahead and define them here so that you will not be one of those people using those terms incorrectly. because you will know that they are not the same as exergonic and endergonic. And those two terms, let's see, I have a little bit more room down here, so I'll write them down here. Those two terms are exothermic and endothermic. So I'm sure that you can already see why people confuse them with exergonic and endergonic. All right, so exothermic is referring to a process that releases heat. And it's right in the name, thermal energy exiting. Okay. An endothermic process then is a process that absorbs heat. And so you might think that all exergonic processes must also be exothermic and all endergonic processes must be endothermic. In some cases that is true, but it's not always the case. And so it's really not a good idea to use those terms interchangeably. Okay. If you were referring specifically to heat, then the terms exothermic and endothermic are the more specific and correct terms. But if you are not specifically referring to heat, then the terms exergonic and endergonic are the terms that you want to use for the release of energy or the absorption of energy. Okay, so we're going to go ahead and erase here and go on to slide 4 now. The rate of a chemical reaction is dependent upon the activation energy barrier. The greater the activation energy barrier, the fewer collisions that will possess the minimum amount of kinetic energy necessary to get over that activation energy barrier, and therefore the rate of the reaction will be slower. If that activation energy barrier is lower, then more collisions will possess the minimum amount of kinetic energy necessary to get over that activation energy barrier, and that reaction will be faster. So there are 3 ways that we can manipulate or speed up the rate of a chemical reaction. One is by increasing the temperature. So I'm going to write 1, temperature. As we increase the temperature, the kinetic energy of the reactant molecules will also increase, which means that not only are we going to have more collisions, but we're going to get more collisions that possess that minimum amount of kinetic energy necessary to get over the activation energy barrier. And we're going to speed up the reaction rate. So let's write here an increase in temperature, I'll just write T, will increase the kinetic energy of the reactant molecules. And this means that there will be more collisions occurring with enough energy to overcome that activation energy barrier. I'll just write E of A. The second thing that we can do is increase the concentration of the reactants. So number 2 here, concentration. An increase in the concentration of the reactants will lead to more collisions. And let's say that only 1% of collisions lead to a reaction. Only 1% of the collisions will have enough energy to get over that activation energy barrier and lead to a reaction. Well, if we have double the number of collisions happening, 1% of that higher number is going to be a higher number. So it is going to increase our reaction rate. So let's write here, increase in concentration, I'll just write C, will increase the number of collisions. And that will increase the number of collisions with enough energy to overcome E sub A, the activation energy barrier. Okay. The last thing that we can do to speed up the rate of a reaction is add a catalyst. I'll just write catalyst. For a catalyst is a substance that can speed up the rate of a reaction without being consumed. If it were consumed, it would be a reactant, not a catalyst. So let's write that here. A catalyst speeds up the rate of a reaction without being consumed. And so you'll typically see catalysts written above the arrow in a reaction. Okay. So that indicates that they're not a reactant and they're not a product. It's a catalyst instead. So usually catalysts work by lowering the activation energy barrier by providing a different mechanism by which the reaction can proceed. So I'm going to write here that a catalyst works by lowering, or I should say, by providing an alternative pathway or mechanism for the reaction with a lower E sub A, lower activation energy barrier. So remember, in our energy diagrams, I'll just make it a generic exergonic reaction. Remember that the activation energy barrier is this barrier right here. This is our E sub A. Okay. So a catalyzed reaction will have the same reactants and the same products, and therefore the same change in energy, the same delta G, but I'll do it in green here. That activation energy barrier, the pathway by which the reaction proceeds will be different, and so that activation energy barrier will be different, and in a catalyzed reaction, it will be lower. So E sub A. This is the catalyzed reaction. Let's label this the uncatalyzed reaction. Okay, it's good to know that biological catalysts are called enzymes. And so when we get to the biological topics in chemistry in future tutorials, we're going to see a lot of enzymes that are going to catalyze all of those biochemical reactions. All right, so this will conclude our tutorial number 14. I hope that you will consider tuning into problem set 14, where we will be drawing lots of energy diagrams and utilizing that terminology, the new terminology, things like exergonic and endergonic and activation energy barrier. Thank you.